Hi, and welcome to AP Chemistry Review. It's me, Dr. V, and we're back to talk about a free response question from the 2022 exam. Specifically, we're talking about question number 7 from the 2022 exam, which was a short free response question, which was scored out of 4 points, like all the short free response questions. If you don't already have your calculator and your periodic table and your formula sheet, go grab them and keep them handy. If you've listened to my webcast before, or maybe you're new, I suggest that you listen to me introduce each part of the problem, and then pause the webcast and try to answer it on your own, and then resume the webcast and listen to my explanation. This also allows you to keep track of your score as you go. Did you earn the point for that part or didn't you? This process is really what's going to help you best advance as a student and really get better at writing high quality responses for free response questions. Right? And that's the goal. That's why we're here. Let's jump right into the question. A Lewis electron dot diagram of the oxalate ion C2O4 2- is shown. And here it is. You were given that. No one expected you to write that on your own. Part A says, identify the hybridization of the valence orbitals of either carbon atom in the oxalate ion. So it doesn't matter if we look at the left-hand carbon or the right-hand carbon, we're going to end up with the same answer. If we look at, say, the left-hand carbon, it's really easy to see that there are 3 electron domains around that carbon atom. And that's true for the right-hand carbon as well. There are 3 electron domains around that carbon atom, and therefore, the hybridization of that carbon atom is sp2. And that's what you needed to write in order to earn the point for part A. Hybridization is a really popular question for AP Chemistry exam questions, so make sure you know that. So I'm going to go a little bit beyond what this question asked us and just do a quick review. Based on how many electron domains, the electron domain geometry, the hybridization, and the bond angles. If you know any one of these, you can work out the others. So if your central atom has 2 electron domains around it, it's got a linear geometry, the hybridization of that central atom would be sp. We're looking at 180-degree bond angles. If there are 3 electron domains around that central atom, like in this problem, the electron domain geometry around that central atom is trigonoplanar. We're looking at sp2 hybridization and 120-degree bond angles. Finally, if we've got 4 electron domains around the central atom, the electron domain geometry is tetrahedral. We're looking at sp3 hybridization of that central atom and 109.5-degree bond angles. It's really helpful if you know this information. It's going to come up a lot. Expect to be asked that somewhere on the AP Chemistry exam. And then the question takes a totally different turn. You're like, oh, it's going to be all about Lewis structures and bonding. No. Part B says, silver oxalate, Ag2C2O4 solid, is slightly soluble in water. The value of KSP for silver oxalate is 5.40 times 10 to the minus 12. Okay, that's a really small number. Okay, and we were given the formula, which is really nice. Part 1 of Part B says, write the expression for the solubility product, KSP, for silver oxalate. Well, they did give us a KSP value, so it's not so surprising that we're going to write a KSP expression. I find when I need to write out an equilibrium constant of any type, especially for KSP problems, it's really helpful to have that balanced equation first. If you weren't given one, you need to generate it. We're going to have our solid silver oxalate as the reactant, and it's going to dissociate to form ions in solution. Specifically, I'm going to form 2 silver ions for each oxalate ion, and that's really important that you recognize that, because if you don't have this right relationship, you're not going to have a correct KSP expression. So it's really important that you do that. Don't skip this step. Trust me. And so we can write a KSP expression. Coefficients become exponents. We leave out pure solids and pure liquids, and so our denominator is 1. And the KSP expression is literally the silver ion concentration squared times the oxalate ion concentration. And this is what you needed to write down for 1 point. It's just the KSP expression. You didn't have to write out the balanced equation. It's just a really good idea. My other comment here that I want to emphasize, make sure you have correct ion charges. Make sure you have Ag+. Make sure that you've written C2O4 2-, and that those ion charges are present in your KSP expression and in your balanced equation if you wrote that too. You don't want to lose points because of those little details, but that could cost you the point. So we just wrote a KSP expression. We have a KSP value. You should be able to predict what's coming next, right? We're going to be asked to calculate the molar solubility of silver oxalate, and that's exactly what they want us to do next. We have the balanced equation. We have a KSP expression. Now we're going to use that. The best strategy to implement here is an ICE table. Now, technically, you don't have to write out the ICE table, but using the ICE table helps you to prevent mistakes that you don't need to be making. Let's set up our ICE table here. We're going to have a column for the silver oxalate, a column for the silver ion, a column for the oxalate ion, and then a row for the initial concentration. How does it change, and what do we have at equilibrium? So initially, we don't have any silver ion in solution. We don't have any oxalate ion in solution. The silver oxalate is a solid. Its concentration won't actually change, so we're just going to ignore it. In order to establish equilibrium, I have to proceed in the forward direction. I have to get some silver ion in solution. I have to get some oxalate ion in solution. But that ratio is really important. That's why we need that balanced equation. If the oxalate concentration goes up by X, the silver ion concentration has to go up by 2X. And that's what we're going to have at equilibrium. It's 2X for the silver ion and X for the oxalate. And we can substitute that into our KSP expression because our goal is to solve for X. So we know the KSP is 5.40 times 10 to the minus 12. I'm going to put 2X in for the silver ion concentration. Notice that we have to square that, and then X for the oxalate concentration. When we simplify this expression, we get 4X cubed. And this is a place where students make lots of mistakes. They forget that 2X squared is 4X squared and then times X. So it's 4X cubed is our relationship here. And then we have to solve for X. Divide both sides by 4, take the cube root, and we get 1.11 times 10 to the minus 4th molar, which I can report to 3 sig figs. That's what we needed to do to earn the 1 point here. Make sure you show work to support your answer. Like I said, the ICE table isn't required. It just helps you. And the last part of the question, the molar solubility of silver oxalate increases when it is dissolved in 0.5 molar perchloric acid instead of neutral distilled water. Write a balanced net ionic equation for the process that occurs between species in solution that contributes to the increased solubility of silver oxalate in perchloric acid. So what we need to do is shift this equilibrium to the right. We want to get more products in solution. We want more ions of silver and more ions of oxalate in solution. The key is that we've got these oxalate ions in solution, but we're doing it in the presence of perchloric acid, HClO4, which is a strong acid. You've memorized your strong acids, right? You've memorized your strong acids, right? If you haven't, start working on that. And we know that acids generate H+ ions or hydronium ions in solution. And the oxalate ion is the conjugate base of a weak acid. And so what we can do is have an acid-base reaction where the H+ ions from the perchloric acid react with the oxalate ions. So essentially we're going to remove oxalate ions from solution. And that's going to end up shifting the equilibrium for the silver oxalate to the right. There are several different ways we could answer this question. So we're going to have 2 H+ ions reacting with an oxalate ion to make oxalic acid. I could write that 1 hydrogen ion reacted with the oxalate ion to make hydrogen oxalate. I do want to point out that states of matter are not required here. That wasn't necessary for the point here. We could also write these reactions in terms of hydronium ion. The same thing, really. Hydronium ion reacting with the oxalate to make oxalic acid, but we're also going to make water when we write it in this form. Or I could have 1 hydronium ion reacting with the oxalate ion to make water and hydrogen oxalate. Any one of these was accepted. It was really important to make sure that your equation was balanced. So states of matter weren't important, but a balanced equation that shows conservation of charge and mass was required, and that you had to have the H+ reacting with the oxalate. And that's what you needed to do to earn the 1 point here. So how did you do on this question? The average score on this question in 2022 was 1.05 out of 4, which makes it the lowest scoring question on the 2022 exam, right? Only about 25%. KSP problems are a gift. So if you're not very comfortable with KSP problems, I would spend some quality time going through them. Maybe even working through my webcast of KSP problems to do more practice with them, because that can be a way to really put yourself ahead of the game compared to other students. If you found this video to be helpful, like the video and leave a comment, and remember to subscribe to my channel so you keep getting all my review materials and really get ready for the AP Chemistry exam. It's always a good day to study AP Chemistry.